Firstly, let's try to make some outline, right? What are we going to do today? And basically, okay, we want to understand the second quantization. Okay, this is the main purpose of quantization. So it's just that if you want to, I don't know, naively define this thing, it's just a representation of quantum, let's say quantum many-body or many-particle states. Okay. So since I said that okay, there's no prior knowledge required, I guess we should pay attention to what we are talking about. So what is quantum, right? What is quantum? What is many particle? What happens when we think, when we consider many particle states, many particle system whatsoever? So in fact, if we downgrade a little furthermore, so what is states? And since this is a representation, so is there any other representation? So I guess there are lots of questions about the state. So, but it's not that hard. Right? This second quantization is not that hard. Actually, if you just understand what we are doing in second quantization, you can just open book and do some calculations without without thinking about what the meaning of it, whatsoever. So it's actually some easy calculations, right? But if you, I don't know, develop some intuition, idea about it, well, I guess we have to just think a little bit. But it's not that hard. So this is why I said that okay, there's no prior knowledge about it. So I guess we should first say that what is states, right? So let's naively say that this. So states is just a mathematical object, I guess. So we use some mathematical objects to define what our system behaves, right? So we are trying to use some mathematical objects to define our states. So in classical physics, for example, right? Classical physics, you can take for single particles, for example, you can define your state as position and momentum of the given particle, right? And we are trying to understand how this thing, mathematical thing, will change according to interactions. So the easiest thing, right? The F force, this is the interaction term, right? It represents our interaction to our states. So momentum of the state will change according to this interaction, and momentum is just m dr dt. Okay. Should I say what is differentiation? Is there a problem with that? No? Okay. So it's kind of a change. Yes, so we solve these two differential equations and we just find a solution, right? A solution. How these states, right, our states will evolve given this interaction. Right? So in quantum physics, however, so the states are well, I will not pay attention to this definition actually. Okay, I must say that, okay, I'm a student at all, right? I do not make these definitions robust, right? I'm not a mathematician. So yeah, I may do some mistakes, so well, pay attention to that. And I generally do not pay attention to, I don't know, correctness, absolute correctness of definitions, wording, whatsoever. So just I try to give some intuition. That's all. Okay. So do not, well, yeah, come up with some other meanings with my sentences. So in quantum physics, I guess the states is just, you can think. States are just solutions of a partial differential equation. Right? the Schrödinger equation. So psi is a function of x and t, right? Plus there is some potential which represent our interaction, right? And we have h bar psi. So if you have you found some function, right, that satisfies this equation, yeah, well, you find the states, right? So the states can be represented, right? Can be represented these wave functions. Okay. Yes. So, and the interaction coming here, right? So this is the interaction point. So, yes. And these are the cool things, right? So if you just take gradients of these potential, you will get the force, right? These are the same thing actually, in function wise, yes, but not correct. There's a minus there. Yes. By using the linearity, since we have some linear function, differential equation here, so we can use the superposition principle. Superposition. So this is states superposition. What is superposition? If you have some solution, well, if you have some psi1, some function, right, satisfies this equation, okay, and in fact, if you have two of them, right, you come up with two brilliant solutions to this wave function. Any linear combination of these two functions is just another solution to wave function, to this partial differential equation, which is, okay, you can combine actually the states, okay, and produce some different states as well. Okay, so is there any question? Did you see these things in lectures? No? No. You're the first students? English. Okay. If you have a question, just ask. Okay? So I just try to communicate. There's no purpose if you don't ask. There are lots of different mathematical procedures that I'm going to use, but if you don't understand that, well, I guess, well, don't ask them. So, you can write them down, right, and search for them. So, if you use separation of variables, the technique, separation of variable, you can find actually there are some special form of these wave functions. These function. Let's say this is I to represent any of these numbers actually. So there are special form of these solutions, right? That satisfies this partial differential equation. Okay, and if you put this form right into this partial differential equation, you will immediately say that okay, this parts depending on x only has a special meaning actually. So let's discuss them first. Okay. Yes. Well, we can immediately see these phi that I define, that I give, I don't know, differentiation of this phi in the second order plus times this function, right, just the potential term, right, will give me these e values. So if you use phi as a subscript, right, yes. So what is the meaning of this? Well, you can define this the part of the left-hand side as an operator, right? And if you apply this operator, there is some differentiation and multiplication with different functions. So this is an operator, right? So let's denote them as H, right? And we apply this as on a function, right? And it produces a function as well, right? If that function is just a multiplication by itself, the input, well, this has a meaning. So in that case, we said that, okay, this is eigenfunction of this operator with an eigenvalue of this eigenvalue. Right? A simple example, for example, well, the exponential of ax is an eigenfunction of the differentiation with an eigenvalue a. It's a simple example. But in this term, in this case, I guess, there is a special differential equation with the given interaction. So this V represents the system, right, the environment, and yes, so the solution of this differential equation actually special for the environment associated with the potential. Yes. Great. Is there any question? No. Nice. So what should I do? So we can think these functions, yes, it is the right time, think this way, yes, as vectors. So they just, well, we can add them together, right? We can add them together and produce new states, okay? So let's try to define some abstract space, right? Including every possible state of this quantum system, right? So if you just define them, right? Just think if there exists. So just think that H is a vector, is a space, right? Is a space or set of every possible states, right? And I will denote every state, every quantum state as this cat notation, right? And I will, as you can see, I can produce every sign actually with linear combination of special states, eigenstates that I just defined. Okay? So you can, it's like a vector, linear combination of vectors. So in order to do, well, you can define a vector with combination of different vectors with some coefficients, right? So you can produce every state, every vector with combination of the special functions. Okay. What I will do is pay attention to Hamiltonian actually. Okay. So in this representation, vector representation, the Hamiltonian is just a matrix, right? So if you apply to some vector, right, it will produce a vector again, but just if you apply this matrix to these special vectors, you will obtain again the same eigenvalue, right, with the initial vector as again. So I guess I can define. I don't know. Is there any restriction to that? I don't know, but I can define my Hamiltonian is just some diagonal matrix, right? With the indices, the diagonal terms are just these eigenvalues. Okay? So I don't know how many states I have. I don't know. But if you just apply to define our vectors as 0, 0, dot, 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 1, 0 again. This is the ith position. If I define these psi i's as these I don't know, unit vectors, as you can see, if multiplication of these matrix and vectors, it will produce the eigenvalue, which is located in the diagonal parts, right? Yes. So if you think like this, the psi is just some column matrix, right, with indices equal to these coefficients. That's it. And I will define these states vectors normal. So the magnitude of every vector will be 1, as it's defined here. So if that happens, I can say if that happens, and if I want to, my psi vector every state is normalized to 1, right? Similar to these special states, eigenstates. If I want to declare this, it will immediately say this form. So these are column vectors, right? With its indices C1, and this will be, I guess, row matrix with indices complete computation of these coefficients. So yes, in order to give a meaning give a meaning to this case. So I sum j, Cj, psi j here, right? So this is psi, the left part, right? The first thing. Second thing is a row part, the column part. And the summation of these things, if I declare these wave functions as just orthonormal, which is just multiplication of these two vectors will produce 1 if I equal to j, 0 if, well, I is not equal to j. Okay. So if this is defined by n, every coefficient of these things, the absolute square of every coefficient, the summation of absolute square of every coefficient will be 1. Okay. So why I do these things? I guess I will understand why I do these things if I just try to apply this H operator on psi, on this made-up quantum state, made up with a linear combination of the different eigenstates. So let's try to give a meaning on this Hamiltonian. So this is just a representation, some operator representation of the system, right? And these eigenstates are just special states that gives some numbers, some EIs. And if you construct all of these very carefully, these Hamiltonian actually will give us the energies. Okay, so these are special states having definite energies, some quantized energies. Okay, so if you apply Hamiltonian on some linearly combined, a general quantum state, you will not observe some definite quantum energy, some quantum state, quantized energy. We can immediately see what you will obtain with coefficients Pi, psi I. So it is not an eigenfunction. Like there is no E energy times psi. So it's not equal to that, right? So this is not a special state actually, but does not make any sense, right? So we defined our states as, I don't know, well, I just made up some equation, right? I just wrote some equation and I declared that the solutions of these equations are just states in quantum world. And by using superposition principle whatsoever, so I have a freedom to define any state with linear combination of these special eigenstates. But only these eigenstates have real energies, right? But any other thing, any other linear combined states does not have independent energy actually. So it does not make any sense, right? You just put a quantum state, quantum particle in a Hamiltonian, right, in a system, but you cannot understand what the energy value it has. So but what we can do, just a pure guess, I guess, at this point, we can measure, we can construct some analytical value by multiply this column vector with a row vector, psi naught, as we did over there. So if you calculate these things, what you will see is just this. So I guess we can guess or we can make up some meaning about these coefficients now. So we have some bunch of coefficients, right? And so square of combination of every square of every coefficient is equal to 1, and the these so square of every coefficients, if multiplied with the relevant energies, it will give us some energy, right? So I will declare them this as probability, right? Probability of our quantum particle represented as these states be inside these ith quantum state. So this is the energy associated with the eigenstate. So this is, by definition, is just mean of energies, right? So we just sum every possible values for energy and multiply every possible values with the associated probability. And if you just sum these things, this is by definition, right? This is probability theory. Probability theory. And this just gives us the mean of energy, average energy of these quantum states. So these coefficients has a meaning, has a kind of a meaning. S square of these things are related to probability of finding our quantum particle that is represented with psi be inside the ith special state, special vector, eigenvector. Okay, is there any question? No. So yes. So I said that psi is just linear combination of these special states, right? So I would just say that these coefficients can be calculated as this. Okay, and we will discuss what is the meaning of this. So if I put this definition, just take it, right? Take this definition, and if you just put this definition inside this thing, right? You will immediately see the part inside the bracket is just an identity. What it says, if you have a vector, right? If you have a vector, some vector, right? I don't know, psi, right? And if you try to multiply this vector with the associated row vector, right? For example, 0, 0, 0, 1, or 1, 0, right? If you multiply this row vector with the column vector with indices is I minus 1, I Ci plus 1, like this, right? What you will get is just the coefficient, Ci, right? So, well, you can represent this Ci times, yeah, the same row vector and summation of those things. If you just multiply these two things, you will get a n by n matrix with 1 in the ith diagonal place, right? So if you sum everything, you will get some identity. Believe me or not, it's going to be happen like this. So this thing is identity, okay? So I will not discuss how I come up with this, but well, it's just intuitive. I just wave my hands and I want you to understand this. So this is in mathematical sense. It says these eigenstates, eigenvectors is complete. What is the meaning of this? We can represent every state inside our the vector space, the Hilbert space. I guess I didn't define this. So these vectors are living in a space called Hilbert space, right? So I can represent any vector defined in Hilbert space with just combination of these phi i's, these basis vectors, as you can declare. So if this operation is equal to unity, by mathematical sense, we say these eigenvectors, eigenstates are complete. Yes. And so these Ci coefficients are just projections, right? So as you can see, I'm saying the same thing over and over again, actually. So these coefficients are actually projections on these vectors, the unit vectors, right? And every projection is just an indice of the relevant section of the vectors, right? So I will define some stupid thing, and I will say this. So I can think, well, okay, so from now on, don't think physical things. So from now on, just believe on your knowledge about linear algebra. So if we have some vector space, right, we can define different basis vectors. So we can represent every basis vector with x and y, right? For example, in two-dimensional vector space, right? So we can represent every vector just combination of these 1, 0, 0, 1, right? So you can define any possible state, or for given any a and b, you can define this kind of a unique, actually, if we have some orthogonal basis vectors, you have a unique representation of these vectors. So you can equivalently define a different x prime, is a different coordinate system to define the same thing, right? So you can equivalently use this kind of orthogonal basis vectors. So you can say that, okay, let's try to calculate this thing. So I will not calculate this thing. I do not have the power to make faster calculations, actually. But you can do so, yes? So I will do the same thing. So I will represent, for example, my Hilbert space with basis vectors. For example, phi I, some vectors, right? Equivalently, you can, for example, you can represent the same vector space with different, for example, what is the word? Phi. Let's use the other phi. For example, different vectors, right? So if you do the calculations, you will see yes, okay, let's do this. So I will equivalently use the both representation. So let's use the explicit definition of these coefficients. So sine I, sine, or we can use the other basis and say that this is phi I, again, phi I sine. For example, yes. Yes. In fact, you can find the change, projection matrix. Is this called projection matrix? Is there anyone who's more projection matrix? I guess there was midterm yesterday, and one of the questions related to find these projection matrices. So you can actually find these projection matrices of changing your basis from one to another. So if you want to, I don't know, you just apply this the unit operation, right? Or that's doesn't matter, right? These are both equivalent. These are both usable bases. So we can say this is sine j, sorry, and sine j, and sine I. So this, for example, can be said that a coefficient, right? And the matrix with indices like this will give you the vectors of phi, variation of phi from phi, right? It will just change your basis from one basis to another. Right? Is there any problem with that? No? Okay. Because I will use these things. So, 45 meters is not bad. Here. Okay. No question. Were you familiar with these stuff? I know you guys are familiar with it. Were you familiar with this stuff? These things? No? 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 Are you following? Are you lost? Lost. You can ask questions. It doesn't matter. You can, but I don't want to discuss these things especially, but this part is that actually will be important for me. Okay? So, do you have any problem with that? No? Okay. So, yes. So let's try to, this is just a, I guess, wrap up of quantum physics and quantum mechanics courses. I guess all of them, right? Are you learning this 431, right? Quantum mechanics. Yes. Oh, sorry, you took from research lecture, right? Okay, so you're among the special ones. So I guess I'll learn these things in master courses, not undergraduate, but yeah, I think you should be familiar with these stuff, okay? If you want to work these quantum stuff, a particle, anybody, doesn't matter. So let's try to define. Well, these are all single particle representation, okay? So we have single particle, and we are trying to represent that particle with a state. Right? Well, let's assume that we have two particles, right? Two quantum particles. We can use tensor products, right, to represent these particles. Let's say that there is some state to represent two particles, right? And I will say, for example, the first particle lives in the first orbital, first state, right? And the second particle, for example, lives in the second state, second orbit, right? So this will be a vector, right? living inside a combined vector space. So the first part is living in the first vector space, right? And the second part is just lives in the second Hilbert space. And this Hilbert space represents the states of the first particle, right? And the second one second. So the order represents which particle it represents, but these psi r represents two orbitals. So I guess I can change these y1 and y2, and let's say that this is var phi and phi. Right? These are different states, different orbitals, right? And the first particle lives in this state, second particle lives in that state. It's that easy. So, however, okay, if you have some quantum particles, and in fact indistinguishable quantum particles, so this is the important thing. In this, I don't know how to spell it actually. This thing, indistinguishable, I don't know. And quantum particle. If you have this kind of things, right, which I actually discussed these things, one of them can be fermions, and one of them can be bosons in 3D. 3D. In 2D, there are different definitions, but let's hold it there. Right? Fermions says you cannot put two particles inside a single state. So these phi, variation of phi and phi is cannot be equal for fermions. But bosons, well, you can put two states, two particles in the same state, right? So this is that. The difference between those two things are just that. So yes, but as you can see, there is no indistinguishability for this definition. So this naive definition, there is no indistinguishability, right? Because I put my first particle in this variation of phi state, and second particle in the phi state. So I can easily distinguish them. Right? If you just add, if you define your states properly and add every combination of swapping exchange of particles, you will define a true indistinguishable quantum particle state actually. So what you should do is define, for example, this form. So if you have a probability of the first particle living in the variation of phi state and second particle in phi state, you have some equal probability actually. You should have equal probability of first particle living in the variation of phi state and second particle in the phi state. Okay. So let's recap that these coefficients are just probabilities of these states. Okay. So the square of these absolute square of these two coefficients will be the probability of our quantum particle being inside this state, right? So equivalently says that the first particle have a 1/2 probability living in the variation of phi orbital, or well, I write the same thing. It will be swapped. It should be swapped, right? Or 1/2 part the probability living in the phi state. Okay. And yes, the important thing is this. If you just swap the order, right? So if you can declare, so think about it. What is the constraint of thinking the first particle? First particle is in the first order, and second particle in the second order. Doesn't matter, right? So you can think them. Okay, this would be my first particle, and this would be second particle. You can easily change them, right? It should be indistinguishable in a sense, right? Let's just swap the Hilbert spaces, right, and obtain the same thing, right? So if you just swap these things, it would be trivial to see, but you will obtain same state. Yes, variation of phi. Wonderful, right? So our particles are in fact indistinguishable. Yes, but it should be physically indistinguishable. So, what do I mean? Physical calculations are not related to these quantum states. Okay? So the physical meaning of these quantum states of quantum physics actually is related to the probability or the probability of finding our particles. So if you just take the norm of this sign, you will have 1 over 2 phi, yes, plus 1 over 2. If they are orthogonal, by the way, phi. So this thing should be indistinguishable if you swap them, right? And there is an equivalent definition. Well, you can equivalently use actually the following definition for your states, quantum states for two particles. So we use these these states with a plus in the middle, and we can equivalently say that this states is actually can be used as well, right? So if you just take the norm of this sign, right, the second sign, this minus term will be cancelled out here, right? This will be just square of minus square root of 2, right? So it will be again 1 over 2 again, right? But the important thing actually, with this definition, you cannot have phi is equal to variation of phi cannot be equal to phi, right? Because it will be trivially 0, right? If variation of phi and phi is equal to each other, right? Both terms will be equal to each other again, so it will be 0. So these kind of definitions with a minus sign change when they exchange is used for fermions because it obeys, they are obeying the Pauli exclusion principle, right? And these definitions actually for bosons. Because you can either say this sign here either can be plus or minus 1, right? So minus 1 is for fermions, so plus 1, what should be to plus 1? There's a second option, it would be bosons, right? That's it. Do you have any question for that? Do you understand this thing? No? You guys? No? Is there any problem? You can ask. It would be, yeah, it would be boring if you don't speak until the end. Yes. So, I guess I didn't. Explicitly say that, but if you just swap these Hilbert spaces as we did it for bosons, you will see the sign nu, for example, the swap version will be equal to minus times swap old. So if you exchange to fermions, right, there will be a minus sign pi phase difference, but if you exchange to bosons, there will be no phase difference between states, quantum quantum states. Okay? So, you should really pay attention to these things actually. So, I cannot just choose two vectors from two vector space, Hilbert space, and I cannot declare these two vectors just represents a quantum state with two-body quantum state. You must pay attention to take linearly combined versions of the following chosen states, right? So you have to choose your orbitals first, and then you must add the linearly exchange combination of every possible combination actually to write a true quantum many particle state. So the just combination of two Hilbert spaces will not give us the real vector space of many particle quantum states. Okay, so there is a very restricted regime. There is a subspace for the valid quantum states. Okay, so I will declare these valid quantum states as special states. So I must, again, let me repeat myself. I must choose my many particle quantum states inside this special area of H combination of H1 and H2. Right? So there will be a special area, right? And I will declare this special area as two-body Fock space. Two-body Fock space. Okay. So this portion of the whole vector space will only contain the relevant physical states. And if you do some calculations, simple calculations related to these linear combined versions, you will immediately see the most important thing is just list of orbitals, list of states. So the important thing, just give me these orbitals. So what is these orbitals? If you give me these list of orbitals, I can immediately write some special state, quantum state for your two-body fermion or n-body fermion, and that special state will be inside the special portion of this the whole space, which is called two-body Fock space. Okay. So yes. So the physically important thing is just which orbitals or quantum states lists of quantum states, let's say, is occupied with by your quantum particles, right? QP quantum particles. Okay. The most important thing is this, and yeah, so and I must say that okay, there is some. There's a thing that we cannot consider in these representations, just linear combined versions of particles. So we cannot create or destroy particles in this representation. Destroy particles, but in nature, well, there is such processes, right? So you can just I don't know, you can combine two positron and electron-positron pairs, and you can produce some photons, right? So there are some processes in physics. So we can actually don't conserve the number of particles. But if you have these kind of states, which you have a definite number of particles, you cannot create or destroy them. And you cannot represent these kind of processes. Well, in fact, you can, but you have to vary and margin your Hilbert spaces, or well, you have to deal with very large matrices, and there will be lots of difficulty in calculations. So, this is called first quantization, right? So first quantization is just representing the quantum state of many particle systems with just combinations, a linear combination of occupied orbitals. This is the first quantization. And second quantization says, okay, why do not use these? Well, we are in the restricted space of the all possible solutions, right? So only these solutions are relevant for us for quantum systems. And let's forget about the other things, and let's just focus on these special states, right? And the information that we are going to use is just the occupation numbers, the list of orbitals. So we will only list which orbitals are occupied with your quantum particles. And we will write our quantum states as this, the occupation basis. So you will just write, for example, this is phi orbital, right? And this orbitals, these states are empty, right? And you will put one quantum particle in the phi orbital. This is variation of phi, right? You will not have any other thing, right? It will be go to infinite whatsoever. So you just list the occupation numbers of orbitals. Okay, so this will be either boson fermion, doesn't matter for now. So this will be our quantum state, and I will represent my state by using these things. Okay, it is just equal to that I wrote here, right? Just linear combination of these orbitals whatsoever. You can equivalently write these things in terms of linear combination of orbitals, right? So you can map second quantization to first quantization just easily. Okay? So I just change my language in it. So for these states, okay, remember the Hamiltonian for Hamiltonian was easy operator, and it will gave us the energies for single particles, right? So in these representations, actually, the occupation number is the good operators for us. So you can easily calculate, or you can declare there is some operation acting on these states, right? And it just gives us, for example, occupation for the orbital I, and it will give us the just number, so occupation number. It will be either 1 or 0 for this case, right? So let's just declare them. These operators are exist, okay? What we can do represents the Hamiltonian, actually, for this representation, is just a summation, right? Occupation of every orbital and associated energy. Right? We can represent the Hamiltonian like this. So, for example, let's assume that there is some three orbitals quantum state, right? And you just there's a three orbital, right? You put one quantum particle in the third one particle to the first one, right? What this operation will give us is just the occupation number of 1, this 1, times energy 1, plus occupation number of second orbital times E2, and E3 times E3 times occupation of the third orbital. Right? This Hamiltonian will give us this, and you will see that E total is just the energy of the first orbital, energy of the second orbital, which makes sense, right? Because you just fill three orbitals, the first and third orbitals, and total energy should be the linear summation of these three energy values, right? So this definition works, right? And it's very easy. You should have emphasized it more quickly, actually, if you do some calculations for first quantization for example, for 3 particles, it would immediately be hard to work actually. But in this representation, writing Hamiltonians and anything actually, it would be much easier. Okay, so in fact, Hamiltonian is not the only thing that is important for quantum systems, right? There might be some, well, scattering processes, right? For example, you can shoot some photon here, right? And you can just excite one of your particles, for example, to here, right? There is some process, quantum process related to this. Right? You can shine light, and we can excite the system, right? So there must be some operators actually just equivalently changing your particles from one state to another, so the excite to states, right? So let's say that there is some hopping terms, and we can represent our interactions by using these hopping terms. So let's assume that there is some hopping term, like right, T-Ij, and what it does, the just hops. Let's a quantum particle hops from ith state to jth state. Okay. Yes. Or vice versa. I don't know. Doesn't matter for me. So I can say that any interaction potential, for example, let's say that is just some values and some hopping parameters, right? So the interaction of these H2, for example, may create hopping for between the first orbital and the third orbital, or second orbital, third orbital. And every hopping will be represented with some coefficients. There will be some energy terms for these hopping processes. Okay, so we can do this, and you must pay attention to if you apply some hopping terms to any Fock, the second quantized states. For example, let's say that it hops from 3 to 2, right? You will obtain what? 1, 1, 0 here. And again, this state is just a member of two-body Fock space, right? So these operations can be defined in these special vector spaces because we are not leaving the space. We have initially we did have some two-body, right, in our quantum state, and at finals again we have 2 quantum particles. Okay. Yeah, this is what we can do actually. We can change the orbitals of these quantum particles, or we can measure the occupation of every orbital quantum state. Okay, but we should do more by defining annihilation and creation operators. So we can represent these hopping operators. It hops from I to j, I said, so it just creates some particle and destroy a particle in the ith orbital. So this is just annihilation operator, annihilation. So it just destroys some particle in the ith orbital, right? Annihilation. And this is creation operator. It just creates a particle in the jth orbital. Okay. So if you just destroy the particle from ith space and create jth, so you just hop. Right? You just let the particle hop from I to j state. Okay. And I can define, well, I will declare this, the occupation number actually. Occupation operator is just the combination of these annihilation operator and destruction operator. Why? Because, well, if you do not have any particle in your quantum state, let's say our quantum system contains only one orbital, one state, right? If you try to destroy empty orbital, you will immediately get 0, right? So if you just try to try to measure the occupation number of the same orbital, again, you should have a 0, right? So this definition just works, right? This is why we define these things. And I can say the operation to distraction operator, annihilation operator to some quantum state with n particle in it will give us n minus 1, right? And creation of some particle to in some orbital which contains n many interactions actually is this. So there will be n many particles in beginning. If I destroy one of them, the number of occupation will decrease by 1. And if there is an n-body particle in the orbital, and if I create one more, the number of occupation will increase 1. So if you just apply this A prime and A, you will immediately see that A prime and A is just give me the n, the occupation number. Okay. So by using this definition, so I made these definitions up in order to satisfy this, right? Because this definition, this equality just works for the empty orbital. This is the whole motivation of mine. So, okay, so these definitions works. There was some. Is there any question, by the way? No. How many time? Left. Past. Is 1 hour. Yeah. Okay. I can discuss 13 minutes more, and I will use the formulas that I have derived in the first half, and I will come up with these quantum field Hamiltonians at the end. Is there yes?
Is that T your definition or is it the formula?
Is this the what? Sorry.
Yeah.
This?
Yeah.
Is
it your notation?
My T? I don't know. Is there any such a notation? No? Yes. Maybe mine, I don't know. So I just trying to build some understanding without knowing anything. So there is only 2 possible operations for these states. You can either measure these occupations, or you can just change the occupations, right? While you're sure that you are not leaving this vector space, right? So there's 2 possibilities for these quantum states to be applied while you are conserving the number of particles, basically. So you either change the occupations or you either measure the occupations. And yeah, when I declare this is an option, I can immediately say, well, why not represent these hopping terms by combination of 2 operators? But I guess if you want to do things very correct way, you should pay attention to these operations. So as you can see, the creation and annihilation operator does not conserve the number of particles, right? So you just go out from these vector spaces, right? So if you do consistent or true, mathematically true calculations, you should define your vector space with total Fock space. Actually, this is the Fock space, right? It's combination of every n-body Fock space. So you just add every possible vector space containing n particle, right? and you extend your world in a sense, space of states, and you just do calculations or make operations within the space that you define. You should pay attention to that. So our state will be inside this Fock space, not Hilbert space. This is the Fock space. The actual Fock space is this space. Yes. Yes, so what should I do next? Change of phases, I guess. I discussed this, I discussed that. Okay, so notice that the order of measurement of occupations should not matter, actually. So both of those two things, for example, it will give you 1, right? So the measuring the occupations, the order of occupations should not matter, right? Because these states, let's use the proper quantum physics language, these states are eigenfunctions of both these operations, right? So if you have if the two operators are commute, they do have the same eigenfunctions, or yes, so yeah. The commutation is this Ni and J, this is by definition, right? Ni and J minus Nj and I. So if this is 0, which means the order of applying operators doesn't matter, then an eigenfunction of one of them will be eigenfunction of the other. So it makes sense, right? So I can ensure this, this algebra or the relation between occupation operators by, for example, saying that every I and every J is just commutes with each other, right? And the Hermitian conjugate of these things as well. So you just take a Hermitian conjugate of both sides, you will get a I dagger a J again. Yes. So it will be 0 as well. So yes, and but I must yes, but I must pay attention to what happens when I and J is equal and there is an A dagger over here. So if you use just these definitions, you will immediately see the I dagger will give us n plus 1, and I dagger A was giving me n, right? Because I defined it so, right? You just apply these two things in these orders, you will immediately see these orders will give these kind of eigenvalues, right? And you will immediately see the commutation relation between I and Ij. So if I and Ij, if they are equal to each other, basically, it will give 1 if I equal to J, or 0 if I is not equal to J, right? Okay. So this is that. Okay. The whole thing is actually coming from these made-up definitions, right? These things, everything. So, but here, yeah, that's much. So we have different possibility as well. So we can actually declare the not that, but we can declare A dagger and A dagger A will be 1. If I want this happens, right? And you can easily say N and N commuting again. for I and j, for example. I don't know. Yes, doesn't matter. And I. Same I. There will be some script for these things as well. Right. If this happens, the commutation relation is again satisfied. Okay, but there's a special thing here. If I just look at that, right, and just guess that, okay, let's try to AI and AJ plus AJ AI. The annihilation operator, the summation, well, let's change this order of annihilation operator and add them together. And if that is 0, right, similar to that actually, here. So it was minus here, AJ, AI. It was 0 for here, right? It was a solution for my commutation relation. So I said that, okay, this might help me as well, right? And by just looking this, there's a plus in between. I can just make this relation, right? I can just say that AI, IJ plus AJ, AI should be 0. Why not, right? If this happens actually for every I and for every J actually, you can see for the same I, you cannot for conjugate as well. So it will be 0 for conjugates as well, right? So as you can see, you just add the same thing twice, right? So the creation operator on the same orbital should be 0 to satisfy this relation, right? So this says that creation of particle on the same orbital will give me 0. This is true if we have some fermions instead of bosons. Okay, so this relation, the anti-commutation, it says anti-commutation, and it is represented with curly brackets, I, Ij. If this commutation relation is true, then you are dealing with fermions. But if this commutation is true, then you are dealing with bosons. Because let's try to understand. In the first quantization, the quantum nature of our particles was hidden in the sign between orbitals, right? If I put plus in between, there would be boson. If I put minus, and the quantum state would obey the Pauli exclusion principle, then it became fermions. Here we just list occupations, right? So I don't know whether they are bosons or fermions, right? So I just instead of changing these representation, I just change the operators, the commutation relation of my operators to hide the information about quantum statistics of these many-body states. Okay. Yes. So the annihilation and creation operator, if they commute, you have bosonic quantum many-body state, and if they anti-commute, which the summation of these I and I. This is for I equal to J, if I equal to J, then you will have some fermions instead of bosons, okay? Is this okay? Is it not? It should be okay, but yes. So one last thing. I can, what I said in the first half was this, right? So I can think my particle in the new orbital nu, right? Like this. So it's lambda nu, right? So this is the some basis, right? And I just change my basis, right? I guess I use var phi and phi for these things. Doesn't matter. Phi or phi. Yes. So if your particle in variational phi state, right? You can equivalently write the your particle in phi state, but times some projections coefficients. So it would be equal to actually say that this. So the creation of particle in phi orbital, right, for vacuum can be equivalently found with creation of phi orbital with these coefficients, phi and phi. And these coefficients actually can be calculated with some integral, right? And this is the orbital of phi, and this is the orbital conjugate of phi. This is the orbital of phi. Okay, so you can change your basis actually for different occupation numbers, different orbitals. Right? So I can write the same thing for the annihilation operator as well. You just take the Hamiltonian conjugate of both sides, and you will immediately see, for example, this is the phi orbital or ith phi orbital, for example. This is J, let's say, J, Ji. Yes. So for phi orbitals, the annihilation of operation can be calculated with annihilation operator in the J, right? But complex conjugate of that. So this is phi I, phi j. You just change the order. Okay. I know I just doing lots of different things, but well, I had to. Okay. So let's try to understand what I'm doing here. So I just creating a particle and put this particle on a phi in a phi I orbital, right? It is the same procedure if I just create a particle on different orbitals and just combine them, right? So it's again quantum physics. So you can represent some states, some vector with some orbital, or linear combination of different orbitals in a different basis. It is the same thing, right? So if I use another basis for these creation operators, the position basis actually. Did I mention this? I guess no. Did I mention this position? No. So for an orbital lambda, you can equivalently say you can equivalently use the position basis. So you can represent these quantum states by using these bases of quantum states only localized at R. So these are quantum states localized at R, at position R. Right? So this will be related to probability of your finding your particle at position R, right? But remember, these are coefficients, right? And absolute square of these things will be related to probability. So the absolute square of these things will be related to the probability. And it is indeed the same thing with wave function, right? Wave function of this orbital lambda, absolute square will be related to probability of you finding your particle at position R. Right? So the wave function representation and vector representation is just equivalent things, but just you change your basis, right? These vector states are just states in some abstract vector space, right? And these wave functions are just some kind of a representation, the positional representation of these abstract vectors. It's a bit different, difficult thing to understand actually. So yeah, but if you just understand what is happening here, you will understand almost not everything, but you will convince yourself about anything actually related to quantum physics. So if I do the same thing by using this, if I do the same trick, I will immediately say that the creation of a particle in orbital lambda is actually saying you create a particle, yes, so let's say this is volume, this is volume integral, sorry. Just create a particle position r. Okay. So you just, if you want to create some particle in an orbital lambda or quantum state in lambda, you can equivalently say, you can equivalently create particles at every position with a given coefficient, which will be the wave function. It is the same thing, lambda r. Yes. Okay. So these creation operators actually build field operators. You just create some particle in a position. These are the exact field operators, quantum field operators. Okay. And for example, for any Hamiltonian, for, I don't know, let's say there is some orbitals, right? And right? I said that, okay, I can use this representation for my naive Hamiltonian. I can equivalently say this is AI, gather AI, yes? So I can equivalently say this is just an energy I times, I will just write these representations, so volume integral of R, so creation of R, right? And yes, phi R, yes, and I will add once more again the distraction parts. Yes. I will use the volume integral of r prime at r prime. For example, the distraction at position r prime with wave function, conjugate of wave function r. Right. Let's get rid of these things. Okay. You can say that, okay, for orbital I, sorry. For orbital I. Okay. Remember, the Hamiltonian, not that Hamiltonian, but the first quantized Hamiltonian was giving me this, right? So I can change the order, right? So I can write, whenever I see this term, I can write that. So equivalently, I can use these things, R, this is VI, yes. So it will be R and R prime, no. So H, psi, R, creation operator, destruction operator, and I cannot change the order. prime. Yes. And phi r prime. Yes. Oh, sorry. I will use this. Sorry about that. I will use this operator first at position r. I will use the Hamiltonian, the phi conjugate, the Hamiltonian. I can put the Hamiltonian actually outside of this thing, and I can write the summation inside here, and I will use this at r and r prime. So this will be an r prime again. So this, believe me or not, will be a direct delta, right? And I will get rid of the one of the integration here, for example, r prime, and I will see the Hamiltonian, second quantized Hamiltonian, will be just r. For example, let's write the Hamiltonian of this first part, bx squared br psi r. Okay, this is an operator, second quantized operator. This is an operator. So I can represent the Hamiltonian of the second quantized form, or fermions or bosons, right? By using these these field operators. So what you see here, you just create or annihilate particles, right? And you just measure the Hamiltonian of them, right? So it's just a representation. So quantum field means you just create some particle at some located position. Did you attend the biology seminar? I don't know, but you mentioned the same thing. So quantum field is just excitation of your some Fock space, so your vacuum actually. So actually the electron is just create some electron, some particle at a given position r. It's just that. So the excitation of this Fock space from 0 to 1, for example, in the positional space, let's say, positional basis. This excitation is the electron or bosons. This is the whole thing. So, and this excitation is done by this creation operator at a position r. It will be proportional because I guess there will be infinite between those two things, but it doesn't matter for our purposes. So, if you want to create some particle at position, you can apply these quantum field operators, or equivalently, you can create every possible. You can create electrons or quantum particles inside every possible orbitals, and you can just add the projection or weights to these creation. Okay, so these are the same things. So, and in the quantum fields, we are exactly using these things. Well, maybe not maybe, but generally they do not we do not use the Hamiltonian representation, but Lagrangian. Usually some path integral whatsoever. So if you just want to learn that, you can learn that. But the whole thing is related to this algebra actually. So quantum field is just some operation applied on a state, second quantized state, living in a Fock space. So I guess that's it. Thank you. Yeah.
You magically change from a volume integral to a line integral?
No, yes,
No.
Just that will be volume integral again. Sorry about that. This is r prime. R prime. Yes. So this will be. Sorry, this is just my laziness. I did not drive this, but I can do so. Yeah. you will see, yeah, you will just use these things. The R prime is just equal to that, right? There will be these phi I, R, sorry, the R, phi I, and phi I, R prime here. You will have these things, okay? And the middle parts will be unity. You will get rid of this, and the multiplication with R and R prime will give you that, right? And you will get rid of the one of the volume integral, and you will get the only single volume integral. So let's let me make some quite small word about interactions. So we represent our interactions locally. So quantum fields works locally. As you can see, you just destroy some particle or create some particle at the same position. If you want to, I don't know what terms they are using in particle physics, but you can add any term related to this, any interaction term in your Hamiltonian, quantum Hamiltonian, satisfying some symmetries. If you are, I don't know, particle physicist, you should pay attention to relativistic symmetries whatsoever. But I'm condensed matter physics, so this Hamiltonian just works for me. So, but you can equivalently say, you can equivalently write some quantum Hamiltonian for Dirac equation, for example. Well, in that case, you should write h nu, gamma nu, I guess, multiply with psi again, with psi dagger, but I guess this psi dagger will be, I don't know why, what, I guess there will be some things here, I don't know, there will be mass terms, so I know this was the term. You can create and annihilate your field, Dirac fields. You can write this thing, and you can write quantum field like this. But the interaction term will be related to these things. So you can, for example, write some interaction term. For example, Coulombic interaction term. Coulomb. Interaction of electrons. You can write volume integral of R, volume integral at R prime, and due to some symmetry, you should pay attention to 1/2 here. So you create a particle at R, you create a particle at R prime, and you annihilate at R prime, you annihilate at R again, and there will be some VR prime. There will be Coulomb potential here as a function of R minus R prime. Right. So this is, for example, interaction in quantum field. You just destroy a particle, right, at R first and R prime, right, and you will create again. So you just, what's happening here, for example, it may be like this. So let's say it has definite momentum, right? And there is another different momentum. Let's say, so this is not correct way of writing these things, but it's a good thing to think. So there is 2 electrons, for example, and they just interact at R and R prime, right? So you destroy 2 electrons, and you create another 2 electrons with different momentum, for example. And this just represents how the electrons interact with each other. And the interaction is just Coulomb interaction, right? They just repel each other. This is the same thing. But this is the quantum representation of this classical repulsion between electrons, right? So if you just write these things and you do some calculations, eventually you will come up with nice, good Hamiltonians. But I must say that these kind of Hamiltonians, which you have 2 quantum fields, right? Quantum field operators, distraction and annihilation, you have only 2, right? These are easily solvable. these things are considered as nonlinear, right? You cannot solve them algebraically. So this is why we pay lots of money to these high-performance computers to calculate these things and understand the quantum processes of these fermions, electrons, bosons. You can equivalently write these kind of Hamiltonians representing with WH bosons, right? These are these interactions. You can equivalently write actually quantum Hamiltonian for photons, for non-relativistic purposes actually. So you can write anything, right? You can represent any quantum dynamics, quantum nature, quantum interaction of quantum system, quantum matter particle system by using these Hamiltonians.